So we've introduced derivatives, we have our limit definition of derivatives, right? But as we've seen, that's a bit tedious, a bit hard to use. We don't want to have to find derivatives using limits all the time. So we want to get away from that definition. Well, not the definition, but from that technique for finding derivatives. And in 4.1, we introduced some basic techniques for finding derivatives sort of very quickly, right? Unfortunately, those techniques really only extend so far to finding derivatives of basically polynomials, right? That's what we did last time. We differentiated things that look like polynomials. We want more techniques, right? We still don't know how to handle products of two functions, something like maybe x times e to the x. We still don't know how to deal with quotients, one function divided by another. We don't know how to deal with compositions of functions. And I've mentioned e to the x, but we don't even know how to differentiate exponential functions or logarithmic functions. So that'll be our goal over the next couple of weeks is building up more differentiation rules and really becoming very good at finding derivatives of any function anyone could ever throw at you. So that's what we're doing today. We'll talk about differentiating products and quotients with the so-called product and quotient rules. So suppose I have two functions, f of x and g of x, and they're differentiable, meaning the derivative exists everywhere. Suppose I have these two functions, and someone says, well, let's look at the product f of x times g of x. Well, it would be really nice if this happened. Would be nice if, okay, so I want to take the derivative of f of x times g of x. Right, again, think of this as maybe this function is 2x and this one is x squared or something, and I want to look at the derivative of their product. It would be really nice if to differentiate a product, f of x times g of x, all you had to do was take the derivative of f prime, and multiply that by the derivative of g. That would be fantastic if that's all you had to do to differentiate products. Unfortunately, this is not true. If it was true, that would be the product rule, but it's just not true. So remember that differentiating products is a bit more complicated than that, and I'll give you the formulas right now. So here's the famous product rule. It says if I want to differentiate a product of two functions, what is it actually? Well, you leave the first function alone. So choose one. It doesn't matter which order you write a product, right? So it's f of x, that stays alone, and then you multiply that by the derivative of g. So f of x times g prime of x, and I'm still not done, plus, now I differentiate the first function. So now, plus f prime of x times the second function not differentiated, g of x. Alright, so this is the famous product rule. If you want to differentiate a product of two functions, it's actually a sum. It's a sum of two different expressions, and that expression is the first function times the derivative of the second, plus the derivative of the first function times the second function. So f of x times g prime of x plus f prime of x times g of x. That's the product rule. Unfortunately, it's more complicated than what you'd hope it would be, but it's still not bad to work with in practice. And I was going to say the quotient rule right now, but how about we do some examples of the product rule instead? And then we'll talk about the quotient rule. Alright, so for example, let's say f of x, actually let's not call it f. I'll just give you the function, it's 2x squared plus 1 times 5x minus 2. Alright, so here's my function, and I want to differentiate it. Alright, so I want to differentiate this, and clearly, right, the way it's written is it's written as a product. It's 2x squared plus 1 times 5x minus 2. It is a product of two functions. You can think of this piece as your f, and this piece as your g. Right, so what's my derivative going to be? Well, my derivative is, and I'll write this down in full, it's the first function, 2x squared plus 1, times the derivative of the second function, times the derivative of 5x minus 2. But that's only the first half of the product rule, right? So plus now plus the derivative of the first function, 2x squared plus 1. I'll put brackets around this so it's clear that that's the only thing I'm differentiating, times the second function, 5x minus 2. Alright, so this symbol here, remember this symbol is the differentiation operator. It means differentiate the expression that comes after it. So this is read as the derivative of 5x minus 2. And I haven't done any calculus yet, right? I haven't differentiated anything. I've just written down what the form of the derivative would be under the product rule. Now we'll do some calculus. Now we'll actually evaluate these derivatives. Derivative of 5x minus 2 from last time. This is a really quick and easy derivative. Derivative of x is just 1. Derivative of minus 2 is 0, so this is 5 times 1 is just 5. And this guy, again, derivative of polynomials aren't bad. We've got 2 times the 2 exponent comes down, so 2 times 2 is 4. Times lower the power by 1 is 4x. Plus the derivative of 1, which is 0. So 4x times 5x minus 2. And that is the derivative. We've differentiated. I probably should simplify this. I should group like terms and so on together. So distributing here, we've got 10x squared plus 5 plus 4x times 5x is 20x squared minus 2 times 4 is minus 8x. So this is actually 30x squared minus 8x plus 5. And there's our final answer. Alright, so being able to differentiate products requires that you know the product rule. Right? It really does require it. So commit this product rule to memory, and you'll see that in practice it's actually not hard to use, right? It's just, it breaks this complicated derivative into really just differentiating these two simpler pieces, right? Differentiating each function separately in their correct place in the formula. I do want to point out that mathematics is really all about how you view things though, right? If someone gives you an expression right here, this function I gave it to you as a product, so we had to differentiate it using the product rule. But it's only a product because it's written as a product. One thing you could do is you could FOIL this out, and if you FOIL this out, it's no longer a product, right? It would just be a polynomial, and you wouldn't have to use the product rule. So technically here it wasn't necessary, but still, if it's written as a product, if you're thinking of it as a product, then you use the product rule. Alright, here's another example. F of t is going to be t squared minus 1 all squared. So here's my function, and the question is find the derivative, right? Find a df dt, or I'll just write f prime of t. Again, notice the variable here is t, so I'm going to call everything t, not x. So find the derivative, and first thing you might say is, again, this is what I was getting at the end of the last example, is math is all about how you view your expression, and right now, the way I would view this is as t squared minus 1, then plugged into a squaring function, right? So it's actually a composition. Differentiating compositions requires something called the chain rule, which we'll do in the next section. So I can't think of this as a composition and differentiate right now. Something else I could do is I could just FOIL this out. Right? I could FOIL it out and treat it as a polynomial, and that's probably the easiest way to go, to be honest. But in the interest of doing products and product rules, let's think of this as a product. It's actually t squared minus 1 times t squared minus 1. So if I write it like that, if I think of it as a product, to find the derivative, I'm now going to use the product rule. Right? It's one function times another function. So what's my derivative? Well, f prime of t is going to be the first function, t squared minus 1, times the derivative of the second function. Notice, by the way, notationally I'm using the Leibniz notation for derivatives. I didn't write d over dx here. My variable is t, so it's actually the derivative with respect to t. It's d over dt. Plus the derivative of the first function times the second function. Alright, so again, we haven't done any calculus. I haven't differentiated anything yet. I've just written down the form of the derivative based on the product rule. Now we'll compute the derivatives. We got t squared minus 1 times derivative of t squared minus 1 is just 2t, plus derivative of t squared minus 1 is 2t times t squared minus 1. And yeah, I guess I could write this as 2. It depends on how do we want to leave it in a factored form, or do we want to expand this whole thing? How about I just think of this as, I've got 2 of these expressions, so we'll write this as 2 times 2t times t squared minus 1. Right, I've got 1 of these things, then another of these things, add them together, you get 2 of them, and I'll just distribute this. Alright, this is 4t times t squared minus 1. So we'll leave the answer in that form. You could distribute this if you want, but there's the derivative. So hopefully you're seeing that the product rule isn't too hard to apply as long as you know what the product rule actually is, and then you just have to compute these separate individual derivatives in the product rule expression. Now, full disclosure, the amount of products that I can actually build right now are fairly limited because the only things we really know how to differentiate are polynomials. When we get to the point of differentiating exponential functions and logarithmic functions, then we can do more product rule examples, throwing in more exotic types of functions. So for now, I'll just do one more example, although it looks pretty similar to the first one. How about we call it h? h of x is going to be 5x minus 1 times the square root of x minus 3. Right, and once again, this is a product, so if I want to differentiate it as it stands, the way it's written, I use the product rule. This is probably a good spot if you want to try a problem on your own. Pause the video, try to differentiate this on your own, and then start it up again and see if we get to the same place. Alright, so I'm just going to go right into this. One thing I will do first, though, before I differentiate, is remember, we never work with radicals when we differentiate. We write them in exponent form, so that's x to the 1/2. Square root of x is x to the 1/2. And now we will differentiate. And because we'll start doing derivatives pretty quickly in this class, I'm just going to jump right into this. I'm not even going to write down the full product rule at this point. We'll just take the derivatives as we go. Right? So remember what it is. It's the first function, 5x minus 1, times the derivative of the second. So we'll just differentiate this in situ right now. Derivative of the second, the 1/2 comes up front, 1/2 x to the, subtract 1 from the exponent, minus 1/2, and minus 3 differentiates to 0. Plus, the derivative of the first function, derivative of 5x minus 1 is 5, times the second, times x to the 1/2, minus 3. And I don't really know the best way to simplify this or group these together. Again, simplification is always a bit in the eye of the beholder. Let's just distribute everything and see what happens. So we'll just distribute this out. 5 times 1/2 is 5/2. X times x to the minus 1/2, remember that's x to the 1. So add the exponents together. 1 plus minus 1/2 is 1/2. So that's 5x times 1/2 times x to the minus 1/2. And then minus 1/2 times x to the minus 1/2. Great. Plus, distributing this, 5 times x to the 1/2 minus 15. Alright, so we'll group these together. 5/2 plus 5. 5 is actually 10/2, so grouping them together is 15/2. And because we started with a square root, I'm going to go back to a square root here, just so we match up with our original expression. X to the 1/2 is square root of x. Now we've got minus 1 over 2, right, there's the 1/2. X to the minus 1/2, if I write that as a square root, remember what that is, that's square root of x, but on the bottom in the denominator there. Right, it's 1/2 times 1 over square root of x. And we grouped this guy with that one, so now we're just left with minus 15. And there's our derivative. Alright, so if you paused your video, hopefully you got to the same spot, same place. Depending on how you simplify it though, maybe you decided up here you'd group the 1/2 powers together, and then maybe you, because our lowest power is minus 1/2, maybe you actually factored out the minus 1/2. I don't know. That's one way to go. But in any case, your answer should be algebraically equivalent to this one. So there's the product rule. Now let's do the quotient rule. So this is what I mean by the quotient rule. Now I have a function that's given as a ratio of two functions, as a quotient of two functions, right? It's a rational expression. Well, unless I suppose it's rational if these are polynomials, but it is a quotient, right? It's f divided by g. So one function up top, one function down below. And again, this would be nice. I'll tell you what you'd really want to happen, obviously. Derivative of a quotient, you'd want to just differentiate the top and differentiate the bottom, right? You'd really like this to be true. But just like with the product rule, what you want to have happen here doesn't happen. This in general is not true. Alright, so don't make that mistake. It's more complicated than that. And so what actually happens is the following. It's the bottom function, g of x, times the derivative of the top, f prime of x, minus the top, f of x, times the derivative of the bottom, so times the derivative of g, all over the bottom function, which is now actually squared. There's the famous quotient rule, right? So it's the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Sometimes this is read as, to make this easy to remember, sometimes people say this is low, I'm trying to remember how to write this, low d high minus high d low, all over, sometimes read as low low or low squared. Right? So it's the lower function times the derivative of the higher function, the top, minus the higher function, the top, times the derivative of the bottom, over a low squared, the bottom squared. The order here matters, right? The order matters because we've got a minus sign. If they were added together, you could flip which order you write these, but because it's minus, you need to do this in the right order, right? Otherwise you'll be off by a factor of -1. So it has to be the bottom, low, times the derivative of the top first. Low d high minus high d low over low squared. Say that to yourself several times, commit it to memory, and there you have the quotient rule. So this is really nice because now we can differentiate rational expressions, right? So here's a simple one, 5x plus 3 over 3x plus 10. Right? There's a rational expression, one polynomial divided by another, and up to this point we didn't know how to differentiate expressions like this, right? Because we couldn't handle quotients. But now we can. So we'll take its derivative, right, using the quotient rules. So we've got, what is it? It's the bottom times the derivative of the top, right? It's low d high. So the bottom, 3x plus 10, times the derivative of the top. And again, it's not too hard to do this in situ on the fly, just differentiate that as you go. But I'll write down all the steps, right? So we're not actually doing any calculus right here. This just says the derivative of the top minus the top, 5x plus 3, times the derivative of the bottom. Derivative of 3x plus 10. Right, so low d high minus high d low over, don't forget this piece, over low squared, over 3x plus 10 squared. So all that's left to do is evaluate these fairly easy derivatives, right? We've got 3x plus 10 times derivative of 5x plus 3 is just 5, minus 5x plus 3 times the derivative of 3x plus 10. Derivative of 3x is 3, derivative of 10 is 0, so this is just times 3. Again, all over the bottom squared. And all that's really left to do is simplify this. Let's see if we can do this all in one shot, because I'm about to run out of space here. How many x's do we have? We've got 3x times 5 is 15x's minus 15x's. So those are actually going to cancel. Then we've got 10 times 5 is 50 minus 3 times 3 minus 9. 50 minus 9 is 41. So this is 41 over, oops, what did I forget to do? It's just a copying error, but we had 3x plus 10 squared. This should be 3x plus 10 squared. So 41 over 3x plus 10 squared. And there is our derivative of f. There's f prime. Really, really, really powerful. This derivative, you technically could have found it using the limit definition, but it would take you a long time. You'd probably still be going for another 5-10 minutes at least. Using the quotient rule and the fact that we know how to differentiate polynomials very quickly, it's not a very long process at all to get to here. Alright, so here's another rational function, and the question will again be find the derivative. So find the derivative, let's call it my function name is g, so it'll be dg over the variable is y, find dg dy. Right, which is just alternate notation for g prime of y. And really nothing different is going on here than the first example. We've got higher order polynomials, so the derivatives will be a little bit more interesting. But yeah, let's do this one in situ. So again, what's my derivative? It's low d high, the bottom times the derivative of the top. So 4y squared minus 5 times the derivative of the top. And instead of writing derivative of the top, let's just differentiate it. Derivative of minus y squared is minus 2y plus derivative of 8y is 8. Now minus the top minus y squared plus 8y times the derivative of the bottom. The derivative of the bottom is going to be 4 times 2 is 8. 8 y to the 1 minus derivative of minus 5 is 0. So just times 8y. And then all over the bottom squared. 4y minus 5 all squared. And of course now if you want your answer to look really pretty, depending on the form MyMathLab wants and so on, you would simplify this, but because I didn't specify to simplify our answer, we'll just leave it in that form. It's a very ugly form that obviously can be cleaned up, right? I would distribute all this stuff and group like terms together. But technically, I've done the calculus, right? I've finished differentiating. Everything hereafter is just algebra. So I'll let you finish this problem on your own if you want. But there's the derivative. And we'll do one more example, a harder one. All right, so here's our function. 2x squared plus 3 times 5x plus 2 over 6x minus 7. And I want to find the derivative. So what do? Well, I look at this. I look at the form that it's written, right? I can rewrite this in different forms, right? Admittedly, I can change the form using mathematics and algebra to write this in a different form, But if I don't want to do that, as it's written, it is first and foremost a quotient, right? It's one function divided by another. The one function being this entire product up top, right? It's one function divided by another. So how do you differentiate quotients? Well, you use the quotient rule. So let's do that. So what is it? It's the bottom times the derivative of the top, 6x minus 7 times the derivative, and I won't do this one in situ because this is more tricky, the derivative of the top. So derivative of 2x squared plus 3 times 5x plus 2, alright, minus the top, 2x squared plus 3 times 5x plus 2 times the derivative of the bottom. 6x minus 7 all over the bottom squared. Alright, so we've written down what the form of the derivative should be using the product or the quotient rule, but again, we haven't done any derivatives, right? We haven't actually differentiated anything. We haven't done calculus. We've just written down the form. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now we're going to do some calculus. Now we need to evaluate these derivatives, and here I have the derivative of the top. Well, the derivative of the top is a quotient. Right? So how do we differentiate, or sorry, it's not a quotient, it's a product. And how do we differentiate products? We use the product rule. Admittedly, you could FOIL this out and just turn into a polynomial, it'd be faster. But because it's written as a product, I'm going to use the product rule. So what's the product rule say? Well, the product rule says the derivative of a product is the first function times the derivative of the second. So we'll do 2x squared plus 3 times the derivative of the second. Derivative of 5x plus 2 is 5. Plus the derivative of the first function. Derivative of the first function is 4x times the second times 5x plus 2. And that's it. that's actually all we have, right? Differentiating this, because it was a product, we had to use the product rule. And to save myself some space, admittedly, I did this in situ here. I didn't write down the full product rule again. We just did it in situ. So it was the first function times the derivative of the second plus the derivative of the first function times the second function. And then we move on to our other derivative. We've got minus 2x squared plus 3. I'm really going to have to squeeze this on the board here. Times 5x plus 2. Times, this is an easier derivative. Derivative of 6x minus 7 is just 6. Barely had enough space. All over the bottom squared. And once again, there is the derivative. It's very ugly right now because I haven't simplified, but that's the calculus done. Right, now we just have to do algebra to simplify this. I'm running out of space. Let's see. I will actually simplify this, but I need more space. So, we'll bring this up here. What do we have? I'm going to combine everything in these square brackets first. So we're going to have 6x minus 7 times, we'll do a lot of this in our head. What do we have? We've got, how many x squareds? We've got 10x squareds from this first expression, plus 20 more of them from the second expression. So 10x squared plus 20x squared is 30x squared. So we've taken care of the x squareds. We've got plus 8x. Alright, we've taken care of those terms, and then we've got plus 15. So that is all of that grouped together and expanded out. Then we've got minus looks like here we're going to have to start foiling, but I'll write the 6 out front. So minus 6 times, we'll just FOIL these two things out. We've got 2x squared times 5x is 10x cubed. 2x squared times 5x is 10x cubed plus 2x squared times 2 is plus 4x squared plus 3 times 5x is plus 15x plus 3 times 2 is plus 6. Alright, all over the bottom squared. 6x minus 7 squared. So you can see there's a lot of algebra going into this, but it's just tedious work at this point. This is the point where you definitely want to double check your calculations. I'm pretty sure this first one was all right. As I went through this, I FOILed, right? I did 2 times 5 is 10x cubed, 2x squared times 2 is plus 4x squared, plus 3 times 5x is plus 15x, plus 3 times 2 is 6. And then everything's times 6, which is up front there. So it's looking good. Now we want to start expanding all this stuff. And there's a lot that goes into this, so let's see what we can do. 6 times 30 is 180. Is that right? Yeah, 180x cubed. 6x times 8x is plus 48x squared. 6x times 15 is plus, what is 6 times 15? 90x. Minus 7 times 30 is minus 210x squared. Minus 7 times 8 minus 56. 7 eighths, 56, yes. 56x minus 7 times 15 is minus 105. So there's all of that. Minus 6 times 10, 60x cubed. Remember to distribute this negative to every single term. 6 times 4 is minus 24x squared. 6 times 15 is minus 90x. And then 6 times 6 minus 36. All over the bottom squared. And hopefully we can finish this off on this next line. Let's see. How many x cubes do we have? 180 minus 60 of them, 120x cubed. Alright, x cubes are done. How many x squareds do we have? Quite a few. 48 minus 24 is 24 of them. Minus 210, 24 minus 210 is minus 186, I think, 186x squared. If I get the arithmetic wrong here, I'm sorry. Minus 86. How many x's do we have? We've got 90 minus 56, so that leaves us with 34. Minus 90 is minus 56, I think. Minus 56. That would have been a lot easier if I'd gone in different order there. 90 minus 90, those guys go away, and then we've got minus 56. Okay, and last but not least, minus 105 minus 96 is minus 141. All over 6x minus 7 squared. And we're done. Again, I might have made a mistake. There's a lot of arithmetic that goes into this. The simplification wasn't particularly fun, but it's not calculus. It's just algebra. Right? It's just algebra. We finished our differentiation a long time ago. But my claim is that here's our answer. And again, if my math lab doesn't ask you to simplify, then you don't have to. You could have plugged in that original expression we had instead of this. So last but not least, we ended the last section with some marginal analysis, right? We had if you have a cost function, then your marginal cost is the derivative, the rate of change of cost. If you have a revenue function, your marginal revenue is the derivative of revenue. If you have a profit function, your marginal profit is rate of change, the derivative of the profit. Let's step this up just one more step. So if let's say the cost to manufacture X items, is given by C of X. Alright, so you have a cost function. The cost to manufacture X items given by C of X. You plug in the amount of items you want to produce, C of X outputs the total cost to produce them. Then, the average cost per item, right, average cost per item would be the total cost over the number of items you're producing, right? So C of X outputs the total cost, and the number of items you're producing is X. So it should be C of X over X. And the textbook, I believe, sometimes calls this function C bar of X for the average cost. But what it represents is the cost, C of X, over X. Well then, what's our marginal average cost? Marginal average cost is the rate of change of the average cost, right? So it should be the derivative of C bar of X. And how does that relate to what we're doing? Well, remember, this is really what C bar is, right? It's the derivative of C of X over X. How do you differentiate something like that? Well, you use the quotient rule, because it formally is a quotient, right? It's one function divided by another. So to find this derivative, you use the quotient rule. And completely similarly, you might be asked to find the marginal average profit or marginal average revenue. So to find average revenue, you take revenue divided by X. And then to find marginal average revenue, you would differentiate the average revenue. And again, using the quotient rule. So similarly, for marginal average revenue, profit, etc. And you'll see some homework problems based on this stuff. We'll do some more in class when the time comes. But for now, I think this suffices. So just remember this is what average cost per item is you take the cost and divide by X. And then if you want the marginal average cost, you differentiate that function, typically using the quotient rule. Okay, thanks.